Hello, all. So, today we are going to discuss about a case study regarding the pollution abatement. That is, abatement of pollutants which create the pollution by using an adsorbent. Usually, while using the the adsorbent after the absorption, it has been thrown away and it cannot be regenerated. And the abatement of a pollutant by adsorption. And with this, we are going to discuss about oxidative catalytic regeneration of the adsorbents. So, here, with the introduction part, the adsorption of an organic pollutants. The organic pollutants usually present in water, even soil, and this absorption of the organic pollutants can be done by an activated carbon. We call it as AC. Activated carbon is a carbon material which we obtain by many sources, from wood or from coconut materials, even from watermelon dried weeds. So there are a lot of possibilities to get this activated carbon. So the absorption of this organic pollutant by an activated carbon is a well-established technology. A lot of research potential area found in this, and also the cost is still a prohibitive factor because we have to make an adsorbent by producing the activated carbon. Since we have to try with many number of activated carbons, so the activated carbons cost is not much effective. But nowadays many researchers has found that these activated carbon can be prepared by simple materials like waste agriculture products can also be used to prepare these activated carbons. So for the economic and environmental reasons, the used or spent AC, that is activated carbon, is not disposed. So it has to be recycled and goes several cycle of regeneration. So here the thermal regeneration of activated carbon, there are many methods, but one of them is often used is a thermal regeneration method. The most common process is that we have to heat this activated carbon to a high temperature. Probably the temperature is 800 to 850 degrees Celsius. Consequently, it's usually not conducted in situ. It has been taken out and taken to some other place, and where these regenerated materials, adsorbents, can be used, which makes a significantly contributing an additional cost to regenerate this kind of adsorbent. So, moreover, high temperature, by using high temperature, the regeneration is an economically feasible one in a large scale, not in a small scale, but it has been reported in 88 by Sony Heimer. Almost 500,000 lb of granular AC per year can be regenerated by high temperature regeneration methods, which is found economically useful. So we can combine an adsorption process. So our plan is to combine an adsorption process of pollutants on well-established adsorptions like activated carbon with a periodic low temperature catalytic reagents of adsorbents as an efficient technology for the treatment of dilute wastewaters. So our method is to combine the adsorption process of pollution along with the low temperature catalytic regeneration instead of using an high temperature regeneration methods. So the advantages of these combined technologies of both adsorption of a pollutant and regeneration at low temperature, we found some three major advantages. First one, the process will be accelerated by high concentration of pollutants eluted from the adsorbent. So it accelerates the high concentration of pollutants. The second one, a large number of adsorption regeneration cycle are expected without loss in capacity. So a large amount of adsorption regeneration cycle can be done without loss in their original capacity. The third one, low temperature generation will be conducted in situ. So previously in situ is not its problem, but here we can go for an in situ methods with even a small units of improving economy of the process. But here we have to address some of the technological and scientific problems. Some technological and scientific problems are the strength, capacity, and reversibility of the adsorption. Previously, we are doing with a high strength adsorption. Later, it can be reduced. Capacity to adsorb can also be reduced. Reversibility somewhat not 100% achieved. So all the threes of an activated carbon is impregnated with the catalyst. So it's combined with the catalyst. The choice of catalyst that operates in this low temperature but well below the ignition temperature of an AC. So activated carbon needs some ignition temperature to burn. So we have to maintain the low temperature below the ignition temperature. And also the catalyst should also work well in that particular range. The third one is the energy of contacting the pollutant with the activated carbon and the catalyst. It should be engineered perfectly. Then efficiency of regeneration should be adopted in a proper way in batch and fixed bed studies. So movable or fixed, we have to go for fixed bed studies so that to achieve a proper regeneration methodologies. So in this case study, we discuss about the relevant information of an activated carbon structures, strength of adsorption, catalysis, and catalytic regeneration. Adsorbate catalytic contact modes are simple methods. Alternative regeneration process. So mostly we have to concentrate on strength of an adsorption. Catalytic regeneration are the most important factors to be discussed. So in adsorption and thermal regeneration of an activated carbon. So in this area, we take an example of phenol. When phenol, an organic compound present in the water from the industries or industrial effluents, has been absorbed by an activated carbon, is normally characterized as physisorption at low temperature and chemisorption at high temperature. What is physisorption and chemisorption? Physisorption is physical adsorption, that is, the adsorption taking place just by a weak van der Waals force. It's not a permanent one, it can be removed. This happens at low temperatures. But chemisorption is not like that. That is, the adsorption and the pollutant molecules may get into a chemical bonding. So that particular type of bonding is difficult to remove. So here the problem is chemisorption may take place at a high temperature and physisorption takes place at a low temperature. So it is easy for us to make the things in low temperature even when compared with high temperature, because in high temperature the chemisorption, which makes it difficult for the separation of adsorption materials. So at relatively high temperatures, a long adsorption contact times and high oxygen content, phenol tend to irreversibly adsorb on the carbon surface. Yes. So was discussed by Grant and King in 90s. So relative adsorption at high temperature is very high due to the chemisorption method, type of adsorption. So long adsorption contact time takes place and a high oxidation content reactant. So phenol tend to be irreversibly adsorbed. So it's difficult to separate. A single component adsorption equilibria of phenol on activated carbon are usually described by the Langmuir. So we know that Langmuir adsorption isotope, that is the adsorption is mainly plotted with the pressure. So single component adsorption equilibria of phenols on adsorption carbons are usually described by the Langmuir and Freundlich absorption isotopes. These isotomes, the Freundlich and Langmuir, are the graphical representation of an adsorption, that is X by M, to the pressure, which explains that when the pressure increases, with the adsorption increases with increase in the pressure, but once the critical or saturated pressure is obtained, after that the further increase in pressure will not increase an adsorption. The adsorption curve becomes flattened after that particular saturated pressure. So what it means, the pressure plays a very important role in the adsorptions. So that's what's explained by Langmuir and Freundlich isotopes, was analyzed by Harrington and Cheng, also by Peel and Yang. So this suggests that at high temperatures, due to the oxidation, and the irreversibility should be reversed. So this suggests a reversible adsorption, but actually a desorption experiments have been performed only in a limited number of studies. So a desorption can be induced by the displacement with a compound of a high affinity to activated carbon and or by increasing temperature. So we have to reverse adsorb. The reverse of adsorption is desorption. So for desorption, the things to be performed with a high affinity to activated carbon and by increasing the temperature. So this was studied by Suzuki in 78. He classified adsorbed organics into three groups. So that is organic material which has been absorbed into the activated carbon, being described in three ways. That is according to the characteristics of the thermal regeneration of a carbon. So one is type 1 is volatile compound. It can be easily removed. Then unstable compound and refractory adsorbates is type 2. So probably it's unstable. Type 3 conjugated aromatic compounds with side sign and adjacent OH. This makes somewhat difficult to reverse the adsorption. So type 3 is found to be a difficult one. So with this activated carbon with the sorbed organics undergoes the following scenario with an increasing temperature. So with the increasing temperature, the things may get a change, drying and loss of high volatility. The adsorbent may become dry and the volatile compounds get out of the adsorbent even though it is an organic compound. So below 200 degrees Celsius this will happen. When we taken with the pyrolysis, that is more than 500 and between 700 degrees Celsius, the non-volatile adsorbers to form a char, so they undergoes an oxidation of the residues. So here the first thing below 200 the volatile substance gets out, and after that the non-volatile substance by oxidation of the residue can take place below 700 degrees Celsius, from 500 to 700. So then exposure to higher temperatures are above 700, that is between 750 to 980 degrees Celsius, which leads to an oxidation of an residual material. So the oxidation of the residual material as well as that of a carbon itself. So here we have three processes, and the fourth one is includes oxygen attack on the activated carbon itself, which may alter the pores structure. The pores may be a size of less than 2 nanometer or lost while large pores are created. So these things happens in the thermal regeneration of an activated carbon. So after this, when we discussed about more than 750 degrees Celsius, it is exposed to 750 to 980 leads to an oxidation of residual material as well as that of carbon itself. The carbon itself can undergo an oxidation. So the latter step includes oxygen attack on the activated carbon itself, which may later the pore structure where small pores, that is less than 2 nanometers, are lost while large pores are created. So what happens here? Let me clear about this. So it may alter the pore structure. So after the step which include oxygen attacks, it may alter the pore structure where small pores are lost, then there's large pores are created. So this makes a difference in the adsorption capacity. So other adsorption regeneration methods that have been explored but have not been implemented commercially include a regeneration or oxidation under high oxygen pressure. 10 to 1000 atmospheres. This is a high oxygen pressure that it has been commercially made. So these regeneration methods have not been implemented commercially. So regeneration by extraction with a supercritical carbon dioxide or with an organic solvent like ethanol, and biological regeneration is a major area of study. So the regeneration by the extraction of supercritical carbon dioxide. We use carbon dioxide, make an adsorption, and it goes to a high temperature. How it been removed, or how it happens, or we may take an organic solvent like ethanol and biological reagents. So we undergoes, which we make the activated carbon undergoes regeneration. So here comes the catalytic regeneration. So what we discussed about how the thermal regeneration is taking place. Now we go for a catalytic regeneration. While adsorption and catalysis are well established technologies, adsorption and catalysis. Adsorption, two types, chemical and physics option and chemical option, which have been used to remove the pollutant materials. And catalysis is a process which enhance or which alters the rate of chemical change. So are the main technologies, they are combined for a regeneration purpose. Here in this study we are going to combine these two for regeneration purpose. Has been employed in some few cases and also in this current one. The three configuration of activated carbon catalysis contact were suggested in the previous studies, and now is impregnation of the adsorption with the catalyst provides intimate contact in a single unit. So both have been made contact in a single unit. Then reduce diffusion paths and accelerated desorption rates. These three techniques can be adopted, but it may diminish the adsorption capacity and may to the metal illusion. So the metal illusion should be avoided. By organizing the AC, that is an activated carbon, and the catalyst in layers within the same bed is the next desirable mode of contact. So we are using both in the same bed, a combined methodology. The two may also be organized in separate units or a mode that requires regeneration by desorption. So this are studied by impregnating with some catalyst like titanium oxide, tin oxide, or zirconium oxide, so TiO2, SnO2, and star O2 by Crittenden in 93, and he went for a photoreactive oxide catalyst. So these titanium oxide, zirconium, and tin are photoactive, that is, by the passage of light they become more active and undergoes more reaction. So this can be regenerated with the carbon by an irradiation methods. So a technique which uses desorption of a toxic compounds from an activated carbon by hot water at a temperature up to 200 degrees Celsius and elevated temperatures can also be applied. It's a pretty simple method. The next one is catalytic, which it continues. That is an AC, that is activated carbon, is not usually employed as a support for oxidation catalyst. So it's not a support for oxidation catalyst. In turn, the oxidation catalyst can be used for this. So because of this pyrophority and adsorbed organics. It may be catalytically oxidized directly on a carbon surface under certain conditions, but it is not favored for oxidation of the carbon itself. So it won't oxidize the carbon. The Turk gives a study on this, was an excellent one to understand the things. So catalytic regeneration of this activated carbon with the hydrocarbons that is present in air pollution has also been done by Novak and Trunk. So our concern is by combining these metal oxide catalysts like chromium oxide, cupric oxide, cobalt oxide, vanadium pentoxide, molybdenum oxide and tungsten trioxide were impregnated onto the carbon from their ammonium salt solution will be an apt method. So high recovery of the adsorption capacities were obtained, and it varied with the nature of the adsorbate and the catalyst. So when we take a high recovery of an adsorption capacities, what happens is that the nature of the absorbent can be changed and the catalyst can be changed. Both the nature going on changes, the recovery rate also changes. So it depends upon both the catalyst and also with the adsorbent. Carbon impregnated with an oxides of manganese of iron and a mixture of iron with carbon were used for the adsorption of organic things from a water solution. So there are an inclination of an adsorbent with some metals like iron, copper has also been done. It is studied by Kognovitsky and Padon, also by iron and copper by Prodon in 80s. So in this, the organic material like dyes, surface active agents, and phenols coming out from the industrial effluents as a water solutions can also be observed by these methods. The impregnation of the carbon surface with iron oxide decreases the adsorption of phenol 20 to 30% without affecting the adsorption of a large molecule was an impressive advantage of this. In this catalytic regeneration, high recovery of adsorption capacities was obtained. So the recovery of adsorption capacities was obtained and it varied with the nature of adsorbate. The nature of adsorbate with a complete recovery of toluene or some other organic materials like phenols and catalyst. The carbon impregnated with the oxides of manganese of iron has been reported by Padon and Kognovitsky and the mixture of iron. So later it produces 20 to 30 percentage changes. So this we have been discussed, I think. Yes. So then the preliminary screening of oxidation catalyst was being conducted. We have to conduct this by determining the initial temperature and detectable carbon dioxide concentration appears during the regeneration of phenol loaded carbon samples. So the activated carbon can be mixed with the catalyst or impregnated with the catalyst by copper, CuO, and chromium oxide, iron oxide, nickel oxide, and then examines. And with this iron oxide and copper oxide, it has been found to be more active. That was put by Padon in 80s. So a loading of at least 3 weight percentage of a metal along with this activated carbon particularly the variety of carbon filtrobes 400, was necessary to detect and remove the CO2 concentration from the gas effluent. So, we mean that these methods are well suitable for water soluble effluents to remove organic compounds, and also for gas effluents for removal of carbon dioxide can be adopted to remove the carbon dioxide from air to reduce air pollution. Now we have a catalytic screening. So mixtures of catalytic screening, a mixture of this metal exhibits a great activity than the single oxides. So, as we stated before, the mixing of an activated carbon AC with iron oxide and copper oxide, it's the most promising catalyst used for the removal of carbon dioxide as well as the phenols or toluenes. So, this activated carbon, the most promising catalyst was found to be these mixes, that is Fe2O3 and CuO, either with small additions of chromium oxides. We consider this as sample A and B, or with a carbon pre-treatment by inert silica. Silica is also a good absorbent in order to suppress the carbon ignition, that is samples of C and D. So there are two samples, one is sample A and B, and another one is the sample C and D with inert silica with carbon. The temperature at which the phenol oxidation takes place when an activated carbon catalysis is simply 210 to 230 degrees Celsius, and the temperature at which the oxidation commences is 320 to 360 degrees Celsius. So we have to be careful with these two temperatures. One is 210 to 230, where the phenol oxidation commences, and the carbon oxidation commences in 330 to 360 degrees Celsius. So these were determined by thermogravimetric and differential thermal analysis. So TGA and TTA, so thermogravimetric analysis, that is the temperature changes with time. So when heating, the weight loss may taken. So due to the increase in temperature and a controlled atmosphere, these compounds, certain compounds will split, and they will get the volatile things may get evaporated. We get a different level of peaks. So based on these peaks, we can identify the weight loss and what are the compounds that have been losing during the increase in temperature under a phased control manner. So those things also reported by Matato and Meitel during 90s. So in regeneration efficiency, you look after this, we have a curve like this, time scale with the carbon dioxide concentration. Usually the regeneration efficiency increases at the beginning level during the beginning time. It's sample A, B, C, D. So these levels may slightly increases, and the steep increases there, and the curve flattens and again decreases when time proceeds. So what it means? It means that the regeneration efficiency of carbon dioxide concentration in the effluent is increases sharply, and over the time it flattens, and when time increases, I think most of the carbon dioxide get evolved, so the evolution get usually decreased. So this is also another example, the same evolution for different samples. So So here you saw the different temperature. You see that the carbon dioxide efficiency percentage, time per minute. So what happens is when the temperature is 290, the evolution that its CO2 concentration recovery rate is much more higher, even at a very little time um, happens. So the temperature plays a vital role in producing this regeneration efficiency. So in the regeneration, so we take sample A, B, C, D series, uh, time in minutes, and CO2 is given here from the effluent. So A, B, C, D are the four different materials samples we have taken that based on iron oxide and uh, silica, etc. So this with the change in temperature, so usually the recovery regeneration will be more at high temperatures. Then we discuss the regeneration efficiency based on those curves we have been seeing. The low temperature At low temperature, the oxidative regeneration of an catalyst and adsorption and activated carbon with the phenol can restore almost all of its original adsorption capacity and its surface area even after 10 cycles of regeneration, as in carbon A. So other carbons with approximately the same catalyst content showed similar degree of recovery adsorption capacity and recovered surfaces even after the 5 cycles. So one, uh, at low temperature, with the phenol, almost all its original adsorption capacity after many cycles. The another one, the same catalytic content, shows similar degree of recovered adsorption capacity. So regeneration of a virgin carbon performed for a comparison under the same condition restored less than 40% of adsorption capacity per cycle, and the capacity declined from one cycle to another cycle. So after several cycles it is recovered. It shows that. So in the peak we can see that the recovery rate of almost all the things is almost more. Uh, when low temperature the recovery is somewhat slowly takes place, but after several repetition it happens. But high temperature the recovery is more, but the cycle difference will be varied. So in the regeneration efficiency, A and C were carried out using a gas with different oxygen contents. So no significant differences has been found between the regeneration of a carbon in air and a stream of 5% oxygen and nitrogen. The latter composition may be more desirable to avoid carbon ignition. A slight increase in the surface area and the adsorption capacity is evident in the regenerated activated carbon catalysis sample. So probably these type of less percentage of recovery or regeneration is probably due to the partial oxidation of a carbon by itself due to the unblocking of the things from the carbon pores and by the metal oxide loss during the regeneration adsorption runs. So this is due to the partial oxidation, one, and unblocking of the pores. It can't able to come out, carbon dioxide particularly, and also the loss of metal oxide. So plays a very important role in decreasing the regenerant efficiency. The regeneration run is somewhat explained here. Yes, the recovery of adsorption capacity. Take this 1 and 2. Recovery capacity for A. See, this was higher, and A and C combination is higher here, and also it repeated with the BP. The same A and C is higher. So the combination of A and C with iron and copper oxides are more to be efficient recovery adsorption capacity. So the regeneration process. So finally we are going to discuss about the regeneration process. So in the regeneration efficiency, the regeneration process did not affect the nature of adsorbent. So the regeneration process did not affect the nature of adsorbent. Adsorbents had been recovered only at some higher temperature. The oxidation of thing takes place. While the result for regeneration of an activated carbon, perabsorption with phenol, are an excellent, poor regeneration was achieved with the halogenated phenols. With halogenated phenols, the efficiency gets reduced due to the chemistry options. Oxidative catalytic regeneration performed at 240 to 300 degrees Celsius completely restored the adsorption capacity of phenol on the carbons modified with the catalyst. So even after 10 cyclic of regeneration temperatures are significantly below the AC ignition point, so that can be regenerated, but high temperature, some oxidative reaction can occur with organic compounds. So regeneration efficiency. Under similar conditions, when we run these things in a similar condition, only a partial recovery of an adsorption capacity was obtained. For spending carbons loaded with the parachlorophenol and parabromophenol, but future work with this can increase the technological change and will remove the shortcomings and it will overcome the similar technology. So here we have to demonstrate or explain that destruction of phenols in dilute solution can be achieved in 2 steps of an adsorption AC with the oxide catalyst followed by the gas phase catalyst at low temperature. The regeneration efficiency of the adsorbent will be increased in gas at low temperatures, and impregation of metal oxides for an organic compounds in a dilute solution makes the activated carbon much more effective in using the pollution abatement. So with this conclusion, we can go through these references, and thank you.